Pluto, a distant and mysterious celestial body, was once considered a full-fledged planet within our solar system. It was regarded as an integral member of the Planetary family until recent groundbreaking assertions by well-known astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight. These esteemed scientists have made an astonishing claim. Pluto might be on a collision course with Neptune. But how could such an extraordinary event unfold? What would be the ramifications of such a massive occurrence? Are we observing a remarkable cosmic anomaly? Or is there more to this potential celestial event than meets the eye? Join us as we explore the possible consequences of a hypothetical Pluto-Neptune crash. Pluto, originally classified as a planet and later redefined as a dwarf planet, continues to intrigue and captivate the curiosity of astronomers and scientists across the vast expanse of the cosmos. Research conducted by leading space experts indicates that Pluto's orbit is perilously close to Neptune's. Renowned astrophysicists like Tyson and Kaku have raised concerns about the dangers of a potential collision between these two cosmic bodies, which could pose significant risks to Earth. But how could such a catastrophic event unfold? Pluto's orbit around the Sun is distinct from any other planet in the solar system, requiring an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto has yet to complete even one full orbit around the Sun. But the intrigue doesn't end there. Pluto's orbit is defined by an unusual shape, markedly different from the almost circular orbits of the major planets. Adding to its unpredictability is Pluto's 17-degree inclination relative to the ecliptic plane, making its orbit far more erratic compared to the other planets. This irregularity introduces additional complexity to Pluto's orbital behavior. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune. For about 20 years during each orbit, Pluto actually crosses inside Neptune's orbital path, defying expectations based on their positions within the solar system. This naturally raises the obvious question: why hasn't Pluto collided with Neptune yet? The explanation lies in the gravitational interactions between other planets in the system. The study of Pluto's orbit began immediately after its discovery. Initially, astronomers were perplexed by Pluto's erratic path. Unlike other planets whose orbits align closely with the ecliptic plane, Pluto's path stood out because of its steep inclination and irregular shape. The mystery surrounding Pluto's orbital behavior can be understood through a concept known as the ThreeBody Problem in celestial mechanics, which seeks to understand the movement and interactions of three objects: Pluto, Neptune, and the Sun, under their mutual gravitational influence. This concept is akin to predicting the future positions of these objects based on their current locations and how they influence one another. For Pluto, this problem demonstrates how the Sun, Neptune, and Pluto's orbits interact in a highly complex manner. Important terms like libration, oscillatory libration, and VSK wobbling are essential in solving this puzzle. Scientists hypothesize that the stability of planetary orbits is a result of libration. In the case of Pluto and Neptune, when Pluto crosses Neptune's orbit, their relative positions are offset by about 90 degrees. This separation is crucial in preventing their orbits from aligning and resulting in a collision. Libration, which refers to the vertical oscillation of a celestial object within its orbit, ensures that Pluto is positioned well above the plane of the orbits when it nears Neptune or another large planet, providing further protection from potential collisions. Another important factor in this delicate balance is the VSK wobbling, named after the researchers who first investigated the movement of objects in space. The VSK wobbling describes how the gravitational forces from Pluto, Neptune, and the Sun influence the motion of each body. This intricate gravitational dance ensures Pluto's orbit remains stable even when it follows an unconventional trajectory near the Sun. The VSK wobbling is vital in preserving Pluto's orbital stability over incredibly long periods, despite the apparent randomness of the system. This phenomenon guarantees that despite the seemingly chaotic nature of Pluto's orbit, specific forces and patterns maintain equilibrium, preventing any catastrophic collisions with Neptune or other celestial objects. The ThreeBody problem is central to understanding how objects in space interact with one another, offering insights into Pluto's motion and helping astronomers study the gravitational effects on distant stars, planets, and other celestial bodies. Mathematical simulations from the late 1980s showed that, despite Pluto's erratic orbital features, its trajectory remains relatively stable, with only minor deviations from its initial conditions. These consistent characteristics of Pluto's orbit have persisted over extended periods, allowing astronomers to refine their understanding of its behavior. More recent computer simulations also clarified how larger planets, such as Neptune, Jupiter, and Saturn, influence Pluto's orbit. Neptune shares a unique relationship with Pluto, manifesting in a 2:3 orbital resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit, preventing it from colliding with Neptune. However, Neptune's gravitational pull is not the sole factor at play. Jupiter's massive gravitational field also significantly contributes to the stability of Pluto's orbit. Saturn's gravity further enhances the stability of the outer solar system. Studies suggest that Jupiter's immense gravitational force alone is sufficient to keep Pluto's trajectory stable for billions of years, possibly ensuring it remains on its current path for the foreseeable future. Together, Neptune, Jupiter, and Saturn work in harmony to prevent Pluto's orbit from being disrupted, contributing to the overall stability of the solar system. These irregularities within the planetary system are crucial for maintaining solar system stability. Without these forces, the cosmos would be far more chaotic, with objects like Pluto potentially colliding with other bodies or being ejected from their orbits, causing turmoil throughout the universe. Understanding Pluto's orbit is particularly important, especially as speculation grows about a potential collision with Neptune in the distant future. The complex relationship between Pluto's orbital pattern and Neptune's provides a deeper understanding of how neighboring planetary systems interact. Pluto's case serves as an example of how even seemingly erratic orbits can reach equilibrium through intricate gravitational interactions. The study of Pluto's orbit emphasizes the importance of continuous observation and analysis to ensure humanity's understanding of the universe remains up to date. Exploring space often forces us to confront the strange and unpredictable nature of celestial bodies. Pluto's orbit stands as a testament to this unpredictability, demonstrating how even the most chaotic systems can maintain stability through gravitational forces. The 2:3 orbital resonance between Pluto and Neptune is a key feature of this dynamic. This resonance ensures that, despite their intersecting paths, Pluto and Neptune never collide. This gravitational relationship is a fundamental concept in celestial mechanics, illustrating how even the most erratic orbital patterns can find harmony over time. In addition to Neptune's influence, other massive planets, including Jupiter, Saturn, and even Uranus, help maintain equilibrium within the solar system. Jupiter's colossal gravitational field serves as a protective force for smaller objects like Pluto, preventing them from straying off course. Some researchers even propose that Jupiter's gravity may have prevented Pluto from being ejected from the solar system entirely. These findings highlight the need to understand not only the behavior of individual objects, but also the broader gravitational forces at play within the solar system. While Pluto's orbit remains stable for now, there's always the possibility that changes could occur in the future. Astrophysicists like Neil deGrasse Tyson continue to investigate the universe, uncovering a deeper understanding of the forces that govern celestial bodies' movements. Although a Pluto-Neptune collision remains unlikely, the potential for such an event underscores the constantly evolving and intricate nature of the universe. This reminds us of the necessity for ongoing exploration and research into the forces that shape our solar system. As the study of Pluto's orbit and its interactions with other celestial objects advances, it remains vital for expanding our understanding of the wider universe. Pluto's situation simplifies the complexities of orbital resonance, where celestial bodies' movements are intricately connected. The 2:3 orbital resonance between Pluto and Neptune ensures that, despite their paths crossing, a collision is avoided. This gravitational balance has preserved Pluto's orbit for billions of years, demonstrating how forces within chaotic systems can lead to stable and predictable outcomes. The significance of this resonance cannot be overstated. It serves as a fundamental principle in celestial mechanics, proving that even the most complex orbital behaviors can reach a harmonious balance through gravitational influences. Understanding resonance extends beyond Pluto and Neptune's interaction to the broader dynamics of the solar system. The interactions between planets, dwarf planets, and other objects are crucial for maintaining solar system stability. Jupiter's role is pivotal in the solar system's overall stability. Its immense gravitational influence acts as a safeguard for smaller bodies like Pluto, preventing them from being ejected or colliding with other objects. Jupiter's gravitational pull also extends beyond Pluto, affecting the orbits of asteroids, comets, and other small bodies in the outer solar system. This interconnectedness illustrates how gravitational forces among celestial bodies work together to preserve balance within the solar system. Some researchers even speculate that Jupiter's gravitational force may have played a role in securing Pluto's position in its orbit, preventing it from being ejected from the solar system altogether. This underscores the importance of understanding each planet's role in shaping the solar system's overall structure. The study of Pluto's orbit and its interactions with other planets highlights the dynamic nature of space. While mathematical models and simulations provide valuable insights into celestial behavior, they also reveal inherent uncertainties in predicting long-term movements. Minor changes in initial conditions or slight deviations in gravitational forces can produce vastly different outcomes over time. This uncertainty emphasizes the complexity and unpredictability of space, underscoring the necessity for ongoing observation and analysis. Studying systems like Pluto's offers critical lessons about the balance of forces that govern the motion of celestial bodies. The stability of Pluto's orbit, despite its irregularities, speaks volumes about the power of gravitational forces and the self-regulating nature of orbital mechanics. As space exploration continues, it becomes increasingly clear that understanding the delicate interplay of these forces is essential for uncovering the broader dynamics that govern both our solar system and the universe at large. As the study of Pluto's orbit and its dynamic interaction with other celestial bodies continues, it sheds light on the underlying principles that govern the behavior of the entire solar system. The fact that Pluto has managed to maintain its orbit for billions of years, despite its seemingly erratic path, speaks to the incredible stability created by gravitational interactions. These interactions help preserve the order of the cosmos, even when objects like Pluto appear to be on an unpredictable course. The importance of this balance cannot be overstated, as it plays a fundamental role in preventing catastrophic events within the solar system. Additionally, the research surrounding Pluto's orbit highlights the complexity of space exploration and the need for constant monitoring. Even though Pluto's trajectory seems stable today, future shifts in gravitational influences could cause unexpected changes. Astrophysicists, including experts like Tyson and Kaku, continue to emphasize how interconnected the movements of celestial objects are, and how understanding these relationships is crucial to predicting the future of our solar system. In fact, they argue that even minor gravitational disturbances can cause significant long-term effects, underscoring the delicate nature of cosmic balance. One of the most intriguing aspects of this ongoing study is how Pluto's orbit offers a practical example of gravitational resonance in action. The 2-to-3 resonance between Pluto and Neptune is a clear illustration of how two objects can share overlapping paths without colliding, due to the stabilizing forces at play. Such resonances aren't unique to Pluto and Neptune. Similar relationships occur between other planets and their moons, as well as among asteroids and other objects in the solar system. These orbital resonances prevent chaos by ensuring that objects continue on their defined paths without disturbing one another. Moreover, the role of Jupiter in maintaining the stability of Pluto's orbit cannot be overlooked. Jupiter, with its massive gravitational field, acts as a stabilizing force, preventing Pluto and other objects from deviating too far from their paths. Jupiter's influence extends far beyond Pluto, affecting many bodies in the outer solar system. Its role in stabilizing the solar system highlights the interconnectedness of these massive objects. Without Jupiter's gravitational pull, Pluto's orbit might have been more susceptible to disruption, potentially even leading to its ejection from the solar system. This reinforces the idea that the solar system operates as a delicate and finely tuned system, where each planet and moon plays a specific role in maintaining overall stability. While these gravitational interactions help keep the solar system in balance, they also raise important questions about the long-term evolution of planetary orbits. The fact that Pluto's orbit remains relatively unchanged despite its erratic characteristics demonstrates the self-regulating nature of celestial mechanics. It suggests that even chaotic systems, when left undisturbed, can achieve a stable equilibrium over time. However, this stability is not guaranteed, and slight changes in the gravitational forces acting on Pluto or other objects could potentially alter their trajectories. This possibility emphasizes the importance of continued observation and modeling to understand the forces shaping the solar system's future. The ongoing study of space, particularly through the work of scientists like Tyson, helps us gain a deeper understanding of how celestial bodies interact. Their work helps us refine our models of orbital mechanics and predict how planets, moons, and other objects will behave over time. In turn, these predictions provide valuable insights into the overall dynamics of the solar system and even beyond, into the wider universe. The study of objects like Pluto allows scientists to observe how gravitational forces can govern the motions of celestial bodies over vast periods, ultimately revealing the interconnectedness of the universe. Moreover, the potential for changes in Pluto's orbit in the distant future, whether from the influence of other planets, shifts in gravitational forces, or other unforeseen factors, reminds us of the unpredictable nature of space. Even the most stable systems can undergo changes over time. As we continue to explore the cosmos, we must remain open to new discoveries and recognize the limitations of our current understanding. The study of Pluto and other distant objects provides important lessons in both the stability and unpredictability of the universe. In this context, it is essential to note that while the potential for a Pluto-Neptune collision seems unlikely, it is a reminder that cosmic events can unfold in unexpected ways. The possibility that Pluto's orbit might change, even after billions of years of stability, illustrates the ever-evolving nature of the universe. As astrophysicists continue to push the boundaries of our understanding, they highlight how gravitational interactions can both stabilize and potentially disrupt the paths of celestial bodies. The complexities of Pluto's orbit offer a fascinating glimpse into the dynamics of space. By studying the interactions between Pluto and Neptune, scientists can better understand the forces that shape not only our solar system but also other planetary systems across the universe. These insights help us appreciate the delicate balance that governs the motion of celestial bodies and the ongoing processes that influence their behavior. They also emphasize the importance of continued research and exploration, as our understanding of space is always evolving. In conclusion, Pluto's orbit, with its intricate interactions with Neptune, Jupiter, and other planets, serves as a prime example of how gravitational forces operate within the solar system. While Pluto's orbit remains stable for now, the ongoing study of its trajectory reveals the complexities and uncertainties that shape the universe. The possibility of a future Pluto-Neptune collision, although improbable, is a reminder of the dynamic and ever-changing nature of space. By studying Pluto and other celestial objects, we gain a deeper understanding of the forces at play in the cosmos, which in turn helps us predict the future behavior of other planetary systems, ensuring that our knowledge of the universe continues to evolve and grow.